Okay, I believe we are live. Welcome back to Kerbal Space Program. So after the last stream, I went to go get some funds, um, running a bunch of VIPs up to orbit and back, and built up quite a bit actually. You can see that number at the top. And in the process of accepting contracts, I misclicked and accepted a contract to position a satellite in a specific orbit of Kerbin. And I thought, oh no, that's going to be hard. Well, no, it's not hard. And as it turns out, once I unlocked the proper science to be able to maneuver these little satellites, you need a smaller engine and smaller fuel tanks and so on. It's really something I should be doing and should get a bunch of them up there before we head out to the moon. In fact, there are contracts available not only for going to the moon, which I thought was going to be the next thing. There was a contract, I believe it's already expired, for placing a satellite in a specific orbit around Mun. So, here is our contract, and it says we want to place it in an orbit that is about 4 million meters apoapsis and a little less periapsis, and with a specific inclination and a specific longitude of the ascending node. For those of you that don't know how that works, basically there is a direction in space, the prime vector, which is on the orbital plane. The world itself has a plane that's designated as the ecliptic. And this is the real world, this is Kerbin, this is the only way to do it. You want to set up a common coordinate system that everybody can use to say that's the direction to that star. And that involves having an orbital plane, and then designating a direction along that orbital plane that's, zero longitude. And the longitude of the ascending node is, if you take your orbit, which is, I don't have my camera on. If you take your orbit, you've got your orbital plane here, your orbit is going to go up and down like that. Or maybe it'll go up and down like that. Anyway, the point is that your orbit is going to go up through that plane somewhere and come down through it somewhere. And the only counterexample to that is if your orbit is exactly in the plane. So, how you define an orbit is you start off at this 0 point in the plane, and then you count degrees counterclockwise. In Kerbal Space Program, everything's degrees. Count that counterclockwise until you find the place where your orbit goes up through the plane, and that's called the longitude of the ascending node. Okay. Then, of course, that between longitude of the ascending node and your inclination, that gives you the orbital plane. And now within the orbital plane, we have specified the periapsis and the apoapsis. We need one more number to actually specify an orbit. It's called the argument of periapsis, and it's another angle. That ascending node we got, if you follow along the orbit, you follow that along until you get to the periapsis point, and the angle you sweep out there is called the argument of periapsis. So if you know those three numbers and the radius of periapsis and the radius of the apoapsis, that will precisely define any orbit. You need one more number, which would define where your vehicle is on that orbit. So that's 6 degrees of freedom to define the orbit. You can also define an orbit by knowing your velocity vector and your position vector. Each one of those have 3 components. So, hey, 6 degrees of freedom. So you need 6 numbers to identify a vessel in an orbit, or 5 numbers to define the orbit itself. And we've been given 4 numbers. So I was faced with a choice when I was planning this. I thought, well, I could write some code to get into an orbit that matches this. Ignore the argument of periapsis. Just when I get there, I will adjust my orbit to have the correct periapsis and apoapsis, and I'm done. And that might satisfy the contract. And if it doesn't satisfy the contract, then I will have to get more complicated and adjust my orbit in such a way that my periapsis and apoapsis are at the right distances, and my argument periapsis is right. And that is much more fiddly code. It takes, you have to adjust here, adjust there. You have to bip your orbit around in a bunch of ways because your final correction has to be made when you're at exactly the right radius for your target orbit. It has to be quick enough that the orbit you were on doesn't carry you away from the orbit you need to be on. So, I'm wondering if perhaps not specifying the argument of periapsis here is their way of saying they recognize that dropping a degree of freedom gives us a little more freedom in figuring out the orbit. Anyway, that's the problem. So that breaks down into, go from our parking orbit, which is this big, expand it out to the target orbit. We're going to do a circular orbit at the apoapsis of the target. And then we're going to find the ascending node, and this is the ascending node of the target orbit relative to our orbit, and correct our orbit, change our orbital plane to match. And once we've done that, we will then correct our orbit to have the right periapsis and apoapsis, and we can do that by waiting until we're at the apoapsis and then burning retrograde and pulling our periapsis in, and we're done. It is possible to do this correction in one burn practically anywhere on orbit as long as you are between the apoapsis and periapsis of your target orbit. I will introduce code for that at some point, but this is several phases that it takes to do this. What I want to start with is, with precision, we're in our smaller orbit. I just want to do one thing. I would do one burn that expands our apoapsis out to the right place. And I want that to stop. If I just burn the engine full throttle until I'm at least far enough and shut it off, we are going to overshoot like crazy, because we're talking very high altitudes where very small changes in our velocity turn into very large changes. And I thought, how do I basically want a ratio of if I have this much throttle, how fast does my apoapsis change? And that kind of ground my gears for a while. This is why I spent so long doing math before starting another stream. And it occurred to me finally that I was doing it the wrong way around. The correct way to do it is to say, if my apoapsis were where I wanted it, how fast would I be moving now? That's step one. And step two is burn the throttle to fix our velocity. That's something we've done. Our circularization script does it. You basically say, we want to change our velocity by this much. And then you've got a gain that says, how aggressive do I want to be? So then you say, I want this much acceleration. And you can either do a lot of acceleration for a short period of time, that's a high gain controller, or a little bit of acceleration for a longer time, that's a low gain. So you take your desired change in velocity, multiply it by your gain, and you get back an acceleration. This is the acceleration we want right now. And to get this acceleration, we need to multiply by the mass. And that's the thrust we need. And then we divide by our available thrust, and that's where we want to set our throttle. Okay, simple. We've done this in our circularization code, so we can just lift that little controller right up. So this should be easy, as long as we know how fast we need to be going now to have our apoapsis where we want it. And this is where you dig up an equation called the Vis-Viva equation. And this is the little magic we'll be looking at today. Basically, it comes from two observations. I'm going to take this from the bottom. The first is Kepler's law, Kepler's second law. He states that a body in orbit sweeps out equal areas in equal times. So if you have, if you're close to the focus of your orbit, you're closer into the sun, you're going to move faster. And as you move out, you move slower. And it's such that if you take the triangle, from, not the triangle, the segment of the orbit from the sun to your orbiting body, where you start, along its path and back, you got an area there. And you do the same thing On the other side, you've got an area there. Those areas are the same. And it takes a little bit of calculus, and a lot of people explain this a lot better than I am. But what it comes down to when you start boiling through the math is that the lateral velocity times the distance from the center is a constant for a body in orbit. So if you've got point R1 in the orbit where you're at radius 1 and you're at your V1 is your lateral speed, lateral, not speed along the orbit, and you've got another point somewhere else where you've got another different radial velocity and a different lateral velocity, those two products are the same. Wow, this means that once you know this product, you can take any point on the orbit, know its radius, and compute the velocity. Okay, that's half of it. The other half of it is the specific orbital energy. There are long derivations of this which go into why each term is the way it is and so on, but the orbital energy is the square of the velocity over 2, so it's the specific energy. So this is energy per mass unit. So kinetic energy is mass times the square of the velocity over 2, and we're dividing up the mass. So this is v squared over 2 is the component of the specific energy from kinetic. Gravitational potential energy, it turns out that mgh, this is what everybody learns in high school. Your gravitational potential energy is the mass times the acceleration of gravity times the height above the ground, where your potential energy is 0 and h is 0. And that's really, really great, except it's useless for us. But we want something that varies like mgh, but we can use it for way above the ground and way below the ground. It turns out that the G changes as you go up and down, and you run through the math and you get a horrible expression, and it turns out that if you say orbital gravitational potential energy is 0 at infinity, and then it gets smaller as you go, so it goes negative, so it's a negative quantity which gets more and more negative, and when you hit radius 0, which only would happen if you were at a black hole, you would have infinite potential energy, so infinitely negative potential energy. So this is that gravity well you see. And once you've finished with all the horrible, horrible math, it's mu divided by r. So what we get is this v squared over 2 minus mu divided by r is a constant while you're on orbit. So no matter where you are, if you know r, you can get v. If you know v, you can get r. And v in this case is not the lateral velocity, it's the velocity along the orbit. Well, you're probably thinking, like I was when I first put these together many, many years ago, that, hey, this is just another way of relating the velocity and the radius. And we've already got one of those. We've got here, v1r1 is v2r2, and this is, unfortunately, this is like lateral, and this is like along. Ooh. Okay, so turns out that if you write down this equation for v1r1 and v2r2, and then you use Kepler's second law to eliminate one of the 4 variables, which you can do, you solve the sucker, you simplify it, and you get this equation here. And you have to do a little bit of algebra to get it into this form, but this is the common form you'll see. V squared divided by mu is equal to 2 over r minus 1 over a. That is neat. And you can basically, you say, if you know, A is the semi-major axis, so it's the apoapsis plus the periapsis divided by 2. So if you know, it basically relates V, mu, R, and A. And if you know 3 of them, you can always calculate the 4th one. Well, mu is given by the body. That's cool. So now you have just a V and R and the semi-major axis. If you know the orbit, then again, this says R and V based on those for that orbit. You don't need to go get R and V for another one. You just pre-calculate it. If you know V, you know R. If you know R, you know V. If you know V and R, you can know A. So wow, this means I can calculate V from U, R, and A. Well, if I know the periapsis and the apoapsis, my current altitude, well, there's my correction right there for, what velocity do I need to be at right now so that I have the same periapsis and my apoapsis is, out there. So I'll write a little code. And obviously the first one you come up with is my, I was going to wait to simplify this until I had it on stream. Local total V is equal to, and that's this term right there. That's actually total V squared is mu times 2 over R minus 1 over A, just like you saw in the equation. And basically you take that, you say, well, that's our total velocity, and then we can compute our lateral velocity, which is here. Okay, so I can compute the radius of the periapsis. I can compute the velocity of the periapsis with Vis-Viva. I can then take that velocity, which we know is all horizontal, and compute my horizontal velocity at my current altitude. So rather than just returning V from Vis-Viva, I can return two things. I can return three things. I can return, well, most callers are going to want the total velocity, and other callers are going to want the lateral velocity or the radial velocity or some combination of them. So I did the math a little bit, but let's step this out. So compute the velocity, and I'm going to put this in lateral. Oops, did not want to full screen that. Do the computations in the order that's best to explain them in. So first, compute the velocity at current h1 where compute the velocity at r. Well, we'll comment what the rest of this is. So let's see, KOS, KSP, and KOS use altitude, but math needs radius. So we have to add the radius of the body. Okay, so math wants current radius. So get the current radius, we say radius of the body plus our current altitude. Math wants semi-major axis, which is half of the radii periapsis plus apoapsis radiuses. Radii. Okay, so now we've got R and A, we can go on with the rest of the math. Compute the velocity at R. We're going to want to get the lateral and radial velocities at V. So we could, at this point, just return the total V. But I wouldn't be able to get my laterals and radials, which I will need later. I didn't want to duplicate the function just to get the rest of this, although at some point I may refactor this to have smaller functions that chew up more cycles to compute by basically saying do a call to get our total velocity, do a different call to get our lateral, do a different call to... Okay, so we want the lateral velocity at the apoapsis. Which is, take our R peri, and there's our V peri, which again, this just uses Vis-Viva. And now, compute the lateral velocity at R. You notice I'm saying squirt abs. In real math, you just take the square root because you know that the quantity under the radical is going to be positive or zero. When you're working with computers and you are computing two different numbers and you are subtracting them, there's what's called numerical error. There's rounding errors because floating point is not infinitely precise. And there's always the chance that R2 over R peri is going to be exactly equal to 1 over A, but during the computation you end up rounding one up, round the first one down and the second one up somehow, and this comes out to the square root of minus 1 times 10 to the 20 minus 23rd. So one way to do that is to clamp it to 0, so you say if it went negative, treat it as 0. And the other way to do it is take the absolute value. And my habit, and this is just habit, has been the observation that floating point units can take an absolute value really quick. But clamping negative numbers to 0 is really quick, but not quite as really quick. So my habit is always to use squirt abs when I'm doing things that are the difference of two numbers that might be 0 and might have numerical errors driving them past. So squirt abs is what I wrote everywhere. LMAG, this is by Kepler's second law. So I've got R peri, V peri, I've got my desired R, and here's my desired V from Kepler, which is my lateral. So if you know your total velocity and your lateral velocity, then we can compute local Rmag is, and I am going to lift it out of this. And this is total V2 B mu times what. Okay. So we use Pythagoras' theorem. The hypotenuse of the triangle is the total velocity, which we got up here. We got the square. We need the square of it. We don't need its actual value quite yet. And we subtract out the square of the lateral velocity, and we take the square root. And square abs, because Rmag may in fact be 0, and we may in fact have total V2 being slightly smaller than the square of Lmag squared. So that gets us it gives us two numbers. And I was thinking, what's the best way to return two numbers in KOS? And there's really no way to return two numbers, but I can return a vector. So I thought, hey, we don't know what coordinate system this is in, but we know a radial component and a lateral component. And I'm looking at the XYZ coordinates. Remember, when I think I mentioned this in an earlier stream, KOS uses a left-handed coordinate system. So if you put up your left hand, hold on, my video is going to be reversed. So this looks to you like I've got my left hand up. Okay, if it looks like I've got my right hand up, then let me know and I will post a correction video with me doing it with the left hand. So I'm going to keep saying left hand, and I'm going to have my right hand up. I'm going to be really confused. So you put your left hand up in front of you, your palm, your thumb facing you, palm facing left. And your index finger points up. And your middle finger curls down the direction of your palm. Your thumb is the x-coordinate of the KOS systems. Think of that as the x. Now, no matter how you move your hand, it is an x-coordinate. And how you orient your hand is going to depend on what you're envisioning. But generally, x-coordinate towards you. Y-coordinate is up. And the z-coordinate points off to the right, okay, which gets you x, y, z in a left-handed coordinate system. And this is important because you can bear this in mind when you start doing, I need a vector that is perpendicular to these other two vectors. You're talking about vector cross products, and x cross y is z. So for instance, if we have a velocity vector x along our orbit this way, and a position vector y, which is our position pointing toward me, so I'm facing the planet and my vehicle is going to the right, then x cross y is z. Well, no, I've done that wrong, haven't I? Velocity cross position is angular momentum in a left-handed coordinate system. So I don't think I can bend my hand that way, but we do know x cross y is z, so y cross z is x. So I just need to set up my hand so that I've got velocity on one finger, and let's say velocity on the z vector this way. That's to the right. So velocity to the right and position toward us, so we are on orbit and we're moving to the right, which is be east, right? And this vector z cross x is y. So our angular momentum is going to be up. It's important. Important to bear that in mind. For what we're going to be doing in the future, the most complicated thing we'll be doing is computing two different angular momentum vectors and looking at the angle between them, and then taking their cross product to find the node vector, which is perpendicular to them both, which is where you want to be when you want to adjust your inclination. We may or may not even use that. Anyway, so there's your left-handed rule. I hate looking at myself in a mirror like that. Okay, so I'm going to now unconfuse myself, and I'm going to get my left hand out here again, because this is my actual left hand. The thing is, though, that y goes up. So if I'm going to arbitrarily place my Vis-Viva results in a vector, they are going to be in the x and the z coordinates. And I think that the x coordinate is best, if I just naturally hold up my hand like this. For me, if I'm looking down at the planet's surface from my point of view, then the x coordinate, which comes out towards me, is my radial velocity, and the z coordinate, which points off to the right, is my lateral velocity. And if you want the square root of the sum of the squares, you take the magnitude of that vector and you get your total velocity, which comes back to the square root of total v2 up here. This means that we are doing some extra computation to get us these other two values, but it's less total than if we made 3 calls in a row. What if I just wanted a raw Vis-Viva v? Let's do that. Because I suspect, let's just do at the top. I am going to refactor my code just to use the simple scalar one, because this is too much sugar for a nickel. We are only going to return this. Compute scalar orbital velocity. Don't need to say what frame of reference you're in because it's a scalar. Returns. And all this goes away. Using Vis-Viva v squared over 2 equals 2 over r minus 1 over a. Note, this is velocity along the orbit. So I'm going to go ahead and do some refactoring as we go over the code to go from using Vis-Viva vec::mag to using Vis-Viva v. And if we reduce out all the calls to the vector version of this, let's put it down at the bottom so that my diffs look cool, well, look simple. If I end up totally retiring the vector version, then I end up totally retiring the vector version. Okay, so with this in hand, we should be able to write a script that takes us to match outside. And I'm going to call that a video. We're going to seal this up, and when we come back, we'll start working on applying this. That'll be in the next stream.